so I'm not the chair of this, Mark is. But I just want to talk quickly about, we have a website for open problems now. So the URL is over there and up in the corner now. So it just has a list of open problems that you can look at and comment on if you're signed in, and see comments too. And then if you want to submit an open problem, you can get the text file to submit on this submit page. It'll just lead you to a page where you can download the text file and then email your PDF to either Mark or I. I'll add it to the website. Okay.
Okay, so doing an open problem session now. We have 9 speakers lined up, each of which have at most 8 minutes to present an open problem. So Shai, set up.
Okay, so thanks the organizer for inviting me, and I'm happy to be here. It's my first visit to a privacy workshop conference, I don't know. Yes, so this is, so I will present an open problem, which is also a promo for my Friday talk. So on Friday I will discuss some partial progress in this direction, and this is based on joint work with Noga Alon, Olivier Bousquet, Roy Livni, and Mariante Maliaris last year in Princeton. And one nice thing that was that I had working with these people is that I really realized like the mathematical depth of privacy. So Mariante Maliaris is a model theorist. She deals with very large infinities. Noga Alon is a combinatorialist, and the other are more computer science. Okay, so one basic theorem in statistical learning, so I will explain this term soon. It's a characterization of learnable classes, of learnable problems, and it shows you basically that uniform convergence, I will explain what it is later, so these implications are trivial. Uniform convergence implies proper learning, implies learning, but the fact that they're all equivalent, which also manifests very basic principles in learning. So for example, the equivalence between these two guys is known as the ERM principle, is a manifestation of the ERM principle. I will explain it soon. But it all goes through a mathematical parameter called the VC dimension. And you know, this result, which was accumulated by several authors, is also called the fundamental theorem of packed learning. So it's really one of the basic facts you learn in any statistical learning class. And what we want basically, or conjecture, is a private analog. So I just added private in front of any of the statistical properties of learning. And I changed the VC dimension by a Ralston dimension, which, as we will see, hopefully I'll have time, is an adaptive version of the VC dimension. So let me first just explain what these definitions are. So what is supervised learning without privacy? So we have some domain X, we have some hypothesis class, which are just functions from X to 0, 1, and we have some unknown distribution on examples. So we get to see a bunch of examples, IID sampled from this distribution. For each example, there is a bit indicating the value, the label. And our goal is to output an hypothesis which minimizes the expected loss. And the non-trivial part is that this loss, L of H, is unknown, is the probability, according to the unknown distribution, of having a disagreement. And this is, so you minimize an unknown quantity. What you do know, so the population loss is unknown, what you do know is the empirical loss. And okay, so this is the learning framework. Now we have these definitions, uniform convergence, learning, etc. So what does uniform convergence say? It says that if you see enough examples if you see enough IID samples, then for every hypothesis in the class, the empirical loss, which you know, will be roughly the same like the true loss. Okay, so what you see is what you get. The empirical loss is roughly the true loss simultaneously for each hypothesis in the class. So this is uniform convergence. Learnability tells you that you can basically minimize the true loss from a finite sample. So there exists some bound, some explicit bound. If you see that many examples, then this algorithm based on the sample outputs some hypothesis which minimizes or competes with the best hypothesis in class. And proper learning also requires that the output hypothesis is always in the class, in H. Now, it's clear that, and the last thing is VC dimension, which, okay, this is this parameter. I will explain it more on Friday. For now, just think of it as a combinatorial parameter. But it's clear that uniform convergence implies proper learning, right? If what you see is if all empirical losses are like the true losses, just pick the empirical risk minimizer. This will also be an approximate population loss minimizer. And of course, if you can learn properly, then you can also learn improperly. It's just an extra constraint. And these three things are equivalent via this notion of VC dimension. So now we have private analogs. So what is private uniform convergence? It's the same thing like uniform convergence, only that I require it to happen privately. So what do I mean? So you get to see a sample from the population distribution, an IID sample, and now you want to publish in a private manner another sample. So T is a new sample which is published privately, and you want that, again, all the losses with respect to T will be close to the true losses. So this is very close to synthetic data and sanitization. And of course, once you have private uniform convergence, you have private proper learning, because you can just post-process it with any ERM, not necessarily private. So it's a similar phenomenon like in the classical case. And private learning is just like learning, but you want that the algorithm will be private. And proper private learning is again, also the output is in the class. And then there is Nielsen dimension, which is an adaptive version of the VC dimension. So before, these decision trees had the same variable in each layer. Now it's different. And let me just finish with, again, with the open problem. So yeah, so we conjecture, or I conjecture, that this equivalence holds. And we know some parts, so we know this direction. So we know that every privately learnable class has a finite VC dimension. And we also know that private proper learning is equivalent to private uniform convergence. And I will discuss this on Friday. And let me just mention that Nielsen dimension is deeply related to online learning. So there is also a mysterious connection which comes up in the proofs that I will show between online learning and privacy, which is natural but still mysterious. We don't understand it. And I guess I'm done. Yeah.
Any questions for Shai while Vitaly sets up?
Why did you define privacy as replacing S with T and not? You could also just say that the whole hypothesis is private relative to the sample set it learned from. That the learner is private.
No, so the S and T was in the context of uniform convergence. So now the goal is to publish all losses of all hypotheses in the class, and one natural way to encode it is via sample T. But you can also, so this is synthetic data, you can also talk about sanitization, and then you can somehow encode it in a different way. But since here we just talk about statistical complexity, so it's equivalent. I don't care about computational complexity, so it's just more easier to define it this way.
So if I understood correctly, it's sufficient to show that if you've got finite Littlestone dimension, then there's a private proper learner, then this whole...
The converse.
The other direction.
It's sufficient. So
Your open question is.
The open question is...
The sufficient.
Like, it would be enough to show, to solve the open question,
Yeah.
it would be enough to show that if it has finite little stone dimension L, then that sample complexity is sufficient for like proper learning as opposed to...
or private uniform convergence. So.
But aren't those equivalent already?
Yeah. Yes, it would
That was
suffice.
my question.
Yes.
like,
It would
I
suffice.
don't know if it's any simpler to think about.
Yes, it would suffice.
Hi, I'm Vitaly. So I'm going to also going to talk about something else on Thursday, and it's a different topic. And the talk on Thursday will also have open problems. So if you want more, there will be more on Thursday. So this open problem is related to a model of private learning that came out of a recent joint paper with Cynthia. And it's actually a relatively new open problem, so it might be actually pretty easy to solve. I don't know. So the basic motivation for this model is the sort of the observation that the utility privacy trade-off in the sort of usual way we learn, where you release the model with differential privacy, is not so great, and we now have both empirical evidence for this and also theoretical bounds, where you often have to pay for the dimension. But at the same time, in many settings, sort of the users of these models only need to see predictions. They don't need to see models. For example, if I go into say a hospital, I want to know what my risk of getting a diabetes is. I don't really need to know the model. I just want to know the prediction. Therefore, an alternative way to sort of think about private learning is as follows: is basically have some kind of prediction interface which holds this sensitive data set, and we have some users where each of the users can ask for a prediction on their own point. So a user will send their point, and then from this interface they'll receive the prediction for their point, and they may ask additional queries on additional points, and so on and so forth. And in this setting, to ensure privacy, will require that this entire transcript satisfies differential privacy with respect to the sensitive data set in the usual sense. And many of you might notice that this is actually the way in which many existing systems already operate. For example, if you ask for a credit score, you won't get to see a model. Or if you type a search query into a search engine, again, you won't get to see the model, but it will be predicting based on whatever you're putting in. The other issue is that it's also now known that this kind of black box access to learned model allows one to violate privacy of the data that has been used for training. There are now several attacks which show that you can infer whether data point was used in the data set with high accuracy just by looking at the predictions of the model. So we need to ensure privacy. So in this work, we sort of, again, focus on accuracy privacy trade-off. And perhaps the sort of the simplest question you would ask in this case is, when understanding this utility privacy trade-off, is what if I'm only interested in a single query? What kind of privacy utility trade-off would be achievable? And once you ask it in this way, the model boils down to the following model, which we call differentially private prediction. And one says that a learning algorithm has this property if a learning algorithm which gets a data set and a query point is epsilon differential private prediction algorithm if for every query point the prediction of the algorithm on the data set and this point satisfies epsilon differential privacy with respect to the set S. So now, given this definition, you can apply it to whatever learning problem you're interested in, and we do it for a couple of problems in the paper. So the one which I think is probably maybe one of the most interesting ones is the setting of convex regression. And this setting one has some family of real-valued functions, f, this capital F, which is parameterized by some w, where w is in some convex body in d dimensions. And the goal is as follows: for every distribution p over this labeled points, the goal is to minimize the expected or population risk of the model with respect to some kind of loss function and the true label, and the sort of the setting is convex, which means that the loss of the model for every sort of example, the loss of the model is a convex function of this parameter W, which parameterizes it. To make it a little more concrete, we'll consider a setting where these convex functions are one Lipschitz, and the set of models is the L2 ball of radius 1. Now, the setting which has been well studied in learning, for example, we know that without privacy, you can achieve excess loss or suboptimality when optimizing this objective of roughly 1 over square root of n, and it's optimal. If you were to do this with epsilon differential privacy, we know that you have to pay an additional term of d over epsilon n, so you have to pay for the dimension. And in our paper, we show that one can, in this epsilon differentially private prediction, one can do it with sample complexity of 1 over square root of epsilon n. I don't know, and it's also not hard to see that there is a lower bound of 1 over square root of n and 1 over epsilon n. And sort of the open problem is the gap between these two bounds. And it might not seem like a big gap, but actually it's a kind of the same gap as one sees between the local and the global model, coincidentally, where basically the question is how much privacy do you get without any additional increase in the loss. So if you're aiming for the loss of roughly 1 over square root of n, then our upper bound only allows you sort of a constant epsilon, gives you constant epsilon for free, whereas we cannot exclude anything which is better than 1 over square root of n. So that's the open problem. I don't know, do you have any? Okay, 2 minutes, wonderful. Let me just briefly mention where this upper bound comes from and also why maybe one could hope to get a bound like this. So if you look at what's the sensitivity in this model, the sensitivity would correspond roughly to this notion of uniform prediction stability, which is related to uniform stability, which again, this would be just basically what's the definition, what is the sensitivity of this prediction? It's exactly the largest difference between the values of predictions on two adjacent data sets. So, and we'd say that an algorithm satisfies this prediction stability gamma if this value is upper bounded by gamma on any pair of adjacent data sets and any prediction point x. And what's known about this notion is that you can solve these convex regression problems with excess loss of roughly 1 over square root n, which is optimal, but also with stability at the level of 1 over square root of n. So if you want this kind of just to achieve sensitivity, you can do it with 1 over square root of n. So from this result, just by whatever adding Gaussian noise, you get our result. I mean, in some cases, you might need to first amplify the stability, which can be done in a sort of very simple standard way by just partitioning the data set and running whatever the algorithm you have on each of the separately, and then just getting their prediction, averaging it, and then this will amplify the stability, and then you can get the result in the entire parameter regime. So yeah, that's it actually. Any questions?
Okay, so I'm going to present a kind of a TUI problem, TUI open problem. So I'm not claiming that it has a significant practical motivation, but actually it underlines some meta question that is open, which is basically separation between pure and approximate local differential primes. Like whether there is a separation. So the background is, I'm using really small font here. So suppose we have a finite domain of arbitrary size, but it's finite. And without loss of generality, it's simply the set of numbers from 1 to t. And consider a private distributed set of n users, x1 through xn, coming from this set. Now, like in the local setting, we know we want to, there is an untrusted entity, want to evaluate a certain function, think of this query as some function of the data set. And in only solicit or sort of acquire sort of local randomizations or like randomized versions of the user inputs, and then try to kind of aggregate them in a clever way to estimate this Q of S with as much with smallest possible empirical error or error, the best possible accuracy. And here the local randomization are defined basically in the usual local differential private sense. So we say that epsilon a randomized algorithm R is epsilon delta local differentially private if for all possible inputs x and x prime from the domain and all possible measurable sets of the output range, the induced distributions by these two pairs of inputs are close in the usual epsilon delta sense. And we say that this local randomization is pure epsilon if delta is 0. It's not, okay. Okay, it's better, definitely. Okay, so, well, in the non-interactive or offline setting, when this query is published and all the users knows about it beforehand, there is results that shows that any epsilon, if you give me any epsilon delta local differentially private protocol, I can transform it into a pure epsilon local differentially private protocol. This was been shown, has been shown in a really nice result by Bob Nelson and Stemmer in 2018, and sort of the seed of this result was actually in a joint paper with Adam in 2015. So that's for the non-interactive case. For, to the best of my knowledge, I might be wrong, all the studied interactive settings in local differential privacy, there is no advantage, or there's no separation between epsilon delta and epsilon. Basically, can use this. Can for every epsilon delta local differential private protocol, you can devise analogous pure epsilon with more or less the same accuracy. So here's the problem statement. Now, again, we have a private distributed data set, and now I'm going to define empirical distribution over the data set, simply the relative frequencies for each item in the universe. And simply let's p hat s denote the empirical distribution induced by the data set. Now I'm going to define what is called a linear query over this empirical distribution, and simply it's defined by some vector q from r to the t, where t is the size of the universe. And basically the objective is to estimate the inner product between q and the empirical distribution. So this is non-privately, I can do it easily. Now, the goal here is to answer a sequence of d online queries under local differential privacy. So by online, I mean that it could be the case that the queries are fixed at the server side, but the user doesn't get to see query qj plus 1 until it actually responds to the query qj. So there is this online sequence, and for every qj, users instantiate their local randomizers on qj and their inputs and send some reports, and then the server or the untrusted entity would estimate, provide an estimate for this inner product. And then it proceeds to the next phase where it publishes qj plus 1. Now let me make this kind of a little bit contrived assumption. Suppose that I'm going to denote q, I'm going to let this capital Q denote the matrix whose rows is the queries, the D queries. And so the rows of this matrix is published one at a time. And let's suppose that there is an L2 norm constraint on the columns of these matrix. So basically, each column of Q is bounded in the L2 norm by some R. And this R is published beforehand. Everybody knows about it, but not about the queries. I'm almost done. So the error criterion you can imagine in this scenario, it could be the L2 error or the L infinity error, it's fine, doesn't matter. So basically, L2 error would be simply the sum of squares of the error between the estimate at each step and the true output or the true value of the linear query. You can also consider another variance of error like the L infinity error. Now, there is a simple epsilon delta LDP protocol that achieve roughly about d by n error, L2 squared. Here by L2 error, I mean L2 squared error. Since R is known, basically what you can do is for every query, every user would simply look at the index in the query that correspond to his input and simply add this Gaussian noise to it. And the Gaussian noise doesn't really depend on anything except R. And of course the epsilon delta parameters. And by the properties of the Gaussian distribution, this spherically symmetric, then it really doesn't, this protocol does not really, or this setting does not really distinguish between the online case and the offline case. This protocol would work also, presumably can work in the offline case, and it can work, the same protocol would work in the online case, where you see one query at a time. The question is simply, is there a pure epsilon LDP protocol for the same setting with the same accuracy? I mean, this setting, it doesn't seem that all the sort of the transformation that we know doesn't work in this setting because of the online nature of the setting. There might be other problems which can perhaps kind of indicate the possibility of having a separation also between epsilon, epsilon, delta, and delta. But the underlying question is like, is there a separation? That's it. Thanks.
Question also.
So does the upper bound rely on composition here? Adaptive composition here?
No, it just depends on like if you compile this protocol, the offline case, what you would do is like you would add a Gaussian, like a d-dimensional Gaussian vector with variance about d by epsilon.
So it's okay.
Yeah.
Did flash it for a second.
It flashed for a second. That's why they left because it started flashing.
This is only 40
Hello, so my name is Sofia Raschodnikova, and I will talk about not so new open problem. So it's been open for a few years, so maybe it's time that we make some progress on it. It's about local filters, and it's based on joint work with Madhav Jha, who is now at Amazon. Okay, so the open problem is about local filters. So let me first motivate it. So it's filters or filtering or reconstruction of C-Lipschitz functions. So imagine that we're in the usual centralized model scenario. So we have individuals, we have a trusted server, we have some clients, and the clients want to compute some function on the database, and we would like to work on it maybe in the black box manner. So they send the function in the form maybe of a program to the trusted server, and the trusted server outputs the value of the function in the database plus noise. Right? So, for example, this is how Laplace mechanism works, or derivative mechanisms, like mechanisms based on Lipschitz extensions. The question is, how can we ensure that this function is really C-Lipschitz? So what if this client sends the program and claims that it has Lipschitz constant C? So in principle, if we know that it has Lipschitz constant C, if we know what this program is, we can easily release it. But what if we actually are not sure and would like to verify it somehow or ensure that it's true? So what can we do? So one relevant object here is from the field of sublinear algorithms, which is called local reconstructor, or also local filter. So they were defined with respect to other properties by Alon et al. And Saxon Seshadri, specifically this local model. And so this is kind of the simplest version of this local filter. And I'm going to explain it using the example of C-Lipschitz functions. So we expect to see C-Lipschitz function in our application, right? So basically, the functionality we expect is that we send x to the function. So it's kind of as an oracle, it sends us back f of x. But it might not be the case that this function f has a desired property, that it's indeed C-Lipschitz. So what we can do to ensure that it's C-Lipschitz, we put a filter between the user and the function, right? And then now the user is going to send the query to the filter instead of sending it directly to the oracle for the function. And what the filter can do, it can make several queries, hopefully not too big, not very large number of queries to the function, and get back the answers. And now it's going to think for a little bit and output something. So let's call it g of x. So in the simplest version, so what we would like to make sure is, so g of x, I'm just going to define it as the output of the filter on input x, right? So what we would like to ensure, kind of in the simplest version, is that g is C-Lipschitz. And we need another condition to make it non-trivial. If f was already C-Lipschitz, we're not going to change it. So g has to be equal to f. Right, so this is the simplest version of the filter. So the way I defined it is deterministic, but you can define a randomized version. Okay, so and then it's kind of easy to see how we would use it. So the client would send the program f and also the Lipschitz constant c, and then we would run the appropriate filter. The trusted server would just run it, figure out this function g evaluated x, and this is what it would release using the Laplace mechanism or Lipschitz extensions. So this is kind of the dream world, and the question is how good you can make those filters, right? So basically, this mechanism is obviously differentially private, and if what the client provides is actually C-Lipschitz function, we have the same accuracy as in the original mechanism, right? So Laplace mechanism, whatever mechanism we're using. So, and the running time is dominated by the running time of the filter. So the question is how fast you can make it. So we had, in the paper in which we defined this problem, so we had a filter, so for this space, but you can think about other metric spaces. So what we had is an upper bound on the running time, which is actually exponential in the dimension d. And it turns out that you need exponential dependence on the dimension d, even for filters with additive error. So basically, I didn't define it with additive error. I said that when f is equal, so f is already has the property, then we're just actually not going to make any error. But even if you allow some significant additive error, you need exponential dependence on d. So what do I want? So like, why am I talking to you? So basically, it turns out that the lower bound does not apply in some cases where we can still get good differentially private mechanisms. So if the output function can be not C-Lipschitz with small probability, then the lower bound doesn't apply, right? So, and we still can get epsilon delta mechanisms using such a reconstructor. So this is one case. Another case it doesn't apply is when given a C-Lipschitz function, we reconstruct to a B Lipschitz function, so we change the constant. And if we change it by at least a factor of 2, then the lower bound doesn't apply again. So, and again, if we had a reconstructor in this case, it would still be useful, right? So we're adding some noise anyway, so we could maybe modify the value of the function a little bit also, or maybe not even a little bit. So that's the question. So can we avoid exponential dependence on D with the right relaxation? Right, so you can think about relaxing in terms of B, relaxing in terms of the probability, or maybe even just some subset of the domain on which you can do it. If we can do this, it could be really useful for ensuring in the systems that programs that run are actually C-Lipschitz, and as a result, we can get differentially private mechanisms using them as a black box. And I guess more generally, maybe we can just combine this with some program verification methods to ensure Lipschitzness and privacy. That's all.
Question?
Are there any lower bounds, maybe like sub-exponential in the
for this cases?
For this case?
So for this cases, no. So there is only this lower bound is quite in bulk, so it's maybe like a 10-page proof. Yeah. So and for this cases, there are, I guess, no non-trivial lower bounds.
So would the problem be easier if you kind of use, instead of directly adding noise, you use some kind of proposed best release type of mechanism, so which kind of checks what are the local omnis to ensure that the sensitivity is small locally?
So you're saying maybe let's modify the object somehow, so it's not the filter.
Modify the mechanism that we'll be using on top of it, instead of just directly adding Laplace. We can do a lot of proposals, at least some kind of use local sensitivity. Yeah, just something for which local sensitivity or smooth sensitivity would suffice.
Right. So I guess we can think what would be the right object. So to abstract out exactly what we need from that, right? So yeah. So you could have like a more relaxed object.
Obviously, right? Potentially easier to construct.
Potentially could be easier to construct. Right?
Okay, let's continue with Thomas.
Okay, so some of you have probably heard me talk about this problem before. If you're sick of me talking about it, solve it and I'll stop. So let me start with telling you about the most basic problem. In dp, which is you're given some function, takes input n, outputs a real number, and it has sensitivity 1. Right, and your task is to output this subject to, say, epsilon differential privacy. We know exactly what the result is, the expected error between your algorithm and the true answer. That is going to be theta 1 over epsilon. Okay, great. So that's something we understand. That's something that's been in the literature since 2006. So let me tell you about what I'll call the second most basic problem in differential privacy. So now you have a whole bunch of queries. So query 1 up to query k. And you want to release all of those. Now let's say instead of just the error of one thing, we're going to look at like the L infinity error of the vector of answers and the vector of queries. So under pure differential privacy, we know that we need to have a dependence on the dimension, the number of queries k. So that's something that we know, but we also know that we can do better than that if we relax to something like epsilon delta dp, or like epsilon squared concentrated dp. For this, we have the following result. So So if you add, so this is just adding Laplace or Gaussian noise. And if you just add independent Laplace or Gaussian noise to each individual query and you apply a composition result, you'll get an upper bound that looks like this. You get square root k because you're getting better composition under these relaxed notions of differential privacy. Now where is this square log k coming from? That's just a union bound because you added k samples from Gaussian noise. The worst of those, because of this L infinity error, is going to be log k worse than the best one, and then the average. And we also have a lower bound, which is root k over epsilon. Okay, so you'll notice that there's a gap here. So there's no log k on the lower bound, there is a log k in the upper bound. And you may be wondering, which of these is correct. So I have a partial answer, which is basically we have a better upper bound. So we can turn that log k into a log k. Now, if there's any justice in the universe, that means we can remove it entirely.
Clearly it's log star.
Maybe it's log star, yeah.
Yeah.
You can do that.
So yeah, I have a bounty on this. I think if you remove it, I'll buy you dinner. If you prove a lower bound that has a log or a log star, I'm going to get you drinks. Okay, so that's the statement of the problem. Basically, here's a gap. Let's resolve it. How much time do I have? Can I say a little bit more about how to? 2 minutes. 2 minutes? Okay, so how do these algorithms work? So the way this algorithm works is you just add independent Gaussian noise. And then you can say, well, most of these answers are actually going to be good. There's just going to be a handful of answers, like one of a inverse polylogarithmic fraction of the answers are going to be bad. And it turns out that I can kind of find these guys and fix them using the exponential mechanism or sparse vector. So we can actually go back and fix these bad answers. And that's where you get this log from. So you just need to make sure that you get most of them right. And then you can go back and fix them. This is kind of a messy algorithm. I would really love to have an algorithm that is just a clean noise adding distribution. This algorithm is a noise adding distribution, but you have to really look closely to see it. So if you manage to get rid of the log with a really clean noise adding distribution, I will buy you dinner and drinks. So I think those are the rules. Mark, did you get the rules that I added in the challenge?
They're on the website. So
they're on the website. Okay, you can look up the terms and conditions on the open challenges.
It's the restaurant, right?
There are constraints on the restaurant. It has to be a sushi restaurant. You don't have to get sushi at the sushi restaurant, but it has to be a sushi restaurant.
What about vegetarian people?
And who don't drink?
We'll find a different
Fancy
problem.
smoothies.
Any questions? Yes.
So delta doesn't appear in the epsilon delta list?
Yeah, so I'm just going to pretend that we're using concentrated dp. So you just multiply by root log 1 of a delta to get epsilon delta. So there's no interesting dependence as far as I know on the delta.
And for L2 error, this...
Oh yes, so if you just use L2 or L1 error, then it's solved with the lower bound is tight. We're all good.
So it's the same lower bound for L2, so it's basically...
Yeah.
Okay, thanks, Thomas.
Matt.
I don't
We're very advanced.
It's on this. That's all. Yes, just in case.
Okay. I also refuse to make slides. I just wanted to do maybe a little bit of advertising. I don't know if, how far privacy has gone in this area, but this is just, you could just sort of think of this as basically like optimal smoothing with privacy. It's sort of my general curiosity. So optimal. So I'm biased in the sense that I have particular smoothing problems I'm most interested in, so I'll just list the one that I find that I care the most about. But so the setup is basically as follows. So suppose that I give you data like the following. So I wrote this, I had this on my slides the other day, if you remember. So I have data from some subject I, but I observe that subject at different domain locations. So I think a lot about time, but it could be other sorts of spaces. Right? Right, and so that data is equal to some mean function, right? Plus some noise. Okay. So mu here, this is the mean function. This is what you want to estimate. Okay, and so the t's, right? So I'm going to just say they're in some script t set. And that, so that can be a nice subset of RD, right? So this can be a subset of RD. Or it can even be like a compact Riemannian manifold, if you want to go that route. But anyways, if in either of those cases, we know how to actually estimate this thing in an optimal sense, but not with privacy. So the epsilons, those are subject-specific errors. Okay. And so these guys, we usually think of them as being relatively smooth deviations. And so you can even have IID noise on top if you want. So plus something like delta ij. So that could be like IID noise, just IID in every possible sense. All right. So the sort of cleanest way I know of estimating this and getting some sort of tight rates is to use reproducing kernel Hilbert spaces. Okay, so this is RKHS. So I'm just going to quickly write this down, and then I'll say what the best rate is I know of for, or I'll say what the best rate is without privacy, and then just sort of leave the privacy question open. So if you want to define an RKHS, then you need a kernel, right? So this thing needs to be symmetric and positive definite, right? Once you have that, to statisticians I would have to really explain this, so maybe I don't need to explain it here, but anyways. So if you want to generate the RKHS, then what you need to do is you take some set which consists of all combinations. So you basically take some set where you take this kernel function, you evaluate it at some domain locations, Ti. You take all possible sort of linear combinations. This is sort of a fairly nice set, so this I can choose any AIs and any domain locations, but only of dimension n. Okay. I then equip that set with the inner product, right? So the inner product of like F1 and F2, this is the sum over AI1, AI2, K, TI1, TI2, right? So I can form an inner product for this set, right? And now once I have an inner product, then I can complete it, right? And so the completion of this set, right? So completion of A, this is, I like to call it K, that extra thing, and that's the RKHS. There's a few other ways you can generate them, but that's one way of doing it, right? So you basically start with some sort of nice functions, you have an inner product, and you complete it. Okay, so, all right. So if this mu is inside of this an RKHS, then we know what the optimal estimation rate is, right? And so if mu is in, say, K, right? So by that I mean it's in like some nice ball in K, right? It's not applying off to infinity. Then the optimal rate is the following. I take some estimator minus the truth, square it and integrate it, okay, over the set. And then that rate is, okay, so I'm a statistician, we deal a lot with OPs, so I'm going to use OP. So this is big OP of 1 over n plus 1 over n m, 2h over 2h plus 1, okay? And the h is determined by how quickly the eigenvalues of this kernel function decay. So if you do sort of like a spectral expansion of this guy, how quickly those eigenvalues decay. So the sort of weird thing here is that you get something, so in statistics we call this a parametric rate of convergence, and when m is 1 we call this a non-parametric rate of convergence. And so the interesting thing is that you get sort of both depending on, so what is m? So the j is 1 to m, pi is 1 to n. So you have n subjects and m domain locations. Yeah?
P is D.
P?
Yeah.
This one? That's probability. It's big O, P, so big O in probability. I know you guys don't do like this. So everybody just writes big O. So yeah, so it's to say that this is a random variable, and this gives you the convergence in probability, and that's the best ratio. Right. So then basically the question is, if you want to do this with privacy, what happens to the rate? That's basically it.
And the dimension you would expect only shows up through h.
The dimension. Oh, so the little trick here is that h is can be written like r over d, where r is the number of derivatives for the functions and d is the dimension. So that's Sobolev spaces of this kind are special types of RKHSs. So you can.
So this is a problem that I recently thought of, and it hasn't really been tested. So let's see if someone solves it now or in the coffee break. This is about selection, which is, I think, a basic problem of sort of private optimization. It's about repeated selection. So let me describe what I mean. So selection means that you have some number of low sensitivity queries. You want to select the ones that have the largest value. Let's restrict ourselves to, say, counting queries. So let's say you're given m counting queries. Let me call them Q1 to Qm. And maybe let me write this as a set, and let's say this is the set Q. So I guess I want to find this, but counting queries, each of them is given by a predicate and is counting how many, what's the fraction of things in the database that satisfies the predicate. And you're also given, of course, a database, which I call X, and let's say this lives in some universe to the n, so n element database. And the goal is to select the k queries with the, so k is also parameter you have. The goal is to select the k queries with the largest value. So you want to output some subset S of the queries such that, let me see how I formulated this, such that nothing outside of this set is too much bigger than anything inside of this set. So this is my notion of approximation. So let's say for every I in S and for every J not in S, I want that the value of Qi on database X is at least the value of Qj on X minus alpha. So alpha is an approximation. Okay, so if alpha was 0, this would exactly be maybe slightly complicated way to say that S should be the top k queries. And now I'm allowing error alpha. Okay.
No condition on the size of the set?
Okay.
It can
Thank
be
you.
all or nothing.
Thank you. Of size k. Thanks. Okay. Does that now make sense? Okay. How can we solve this? I basically know two algorithms. One sounds silly, but it actually is a little could be better, depending on Q. So the basic question is, maybe before I describe the algorithms, the basic question is for each Q, what is the smallest n so that I can solve this problem, which is sort of the sample complexity. The smallest n for which this is solvable with, let's say, your favorite notion of privacy. So let's say epsilon delta differential privacy. This is the basic question. Again, the way I've asked it, I'm asking if I give you the queries, what is the best algorithm that you can use for those queries? So the answer may depend on what the queries are. We sort of know the answer if we want to know what is the best thing to do for sort of the worst possible queries. Okay, so now let me tell you what are the two algorithms that I know for this. So one is do either, so okay, these are algorithms. One algorithm is do report noisy max or exponential mechanism k times. Noisy max k times. And let's say analyze it with advanced composition. And then basically whatever Q is, if you're running this algorithm, the sample complexity is that n should be at least something like root k, root log of 1 over delta, if you're doing epsilon delta differential privacy, times log m is the total number of queries again, over, let's say, alpha epsilon. And this is, as far as I know, tight for Q equals all one-way marginals. Maybe Thomas can correct me if I'm wrong. Okay? Good. Okay, so this is sometimes the right thing to do. Another thing you can do is just compute all the queries. So compute Q1 of X to Qm of X. And I won't write it, but select the top K based on computing all of them. And this could sometimes be better. So for example, imagine that Q is threshold queries or histogram queries. So for histogram queries, computing all the queries is better than this. Right? So this sometimes actually beats the algorithm that I think makes more sense, but okay, it's not always optimal. And maybe a more constrained version of this more general question is, I cannot think of any example. By example, I mean an example of an algorithm and queries, I guess, or natural queries, maybe, So that any example, I guess, of an algorithm that beats both on some Q. Both 1 and 2 on some nice Q, let's say. 1 minute? Okay. I don't think I have anything else to say, so maybe I'll take a question.
So you're thinking of K as staying small and the other parameters becoming larger?
Yeah, maybe. Sure. Okay. So no, actually not necessarily. So what I was saying is that this can sometimes be better. This is, I guess, if K is like a little bit large. So let's say all threshold queries we can compute with sample complexity, which is something like 2 to the log star, if alpha is constant. And then if K is like bigger than 2 to the log star, if it's like log, then this is already better. Actually, looking at this, there's a log there anyway, so maybe I didn't need to do all of that. Okay. So maybe think of K as being smaller than the other parameters, but still going to infinity. Other questions? So maybe one set of queries for which I don't quite. Yeah, I can. Let's say if the queries here have some notion of like small VC dimension, does that help in some way? And I'm not sure.
Thanks.
Thanks. So what happens now? Do we leave this here?
With Adam.
Give it to Adam?
So,
This side. Sorry. Oh. Oh, because you lost. And we're, I see. Got it.
because we alternate.
Got it. Got it.
Okay, so I'll talk about adaptive data analysis, with symmetric information. And I'll credit sort of 2 papers by Sam Elder for formulating this problem and saying some of the things we know about it. So this isn't really a problem about privacy, although many of the same people work on it and many of the same techniques come up, as many of you know. So that's why it makes sense to talk about it here. But the problem itself doesn't explicitly talk about privacy. Imagine we've got a data set, call it X. It consists of n records drawn IID from some distribution P. So P is a distribution on some universe U. X is IID and copies of P. We hand this data set to some mechanism, and this mechanism is going to try to answer queries about the data that are coming from some analyst. And specifically, these are statistical queries, or if you prefer, for simplicity, counting queries. So each query is specified by a function from the universe to 0, 1, and this could be either 0 or 1 if you prefer. And now there's sort of 2 directly relevant notions here. There's the answer to the query on the data set. So given a data set X, the value of the query is the empirical mean of Q over over the data points, and but then I can also talk about the value of the query on the distribution, and that's the expected value of this function on a fresh sample from P. Okay. So the mechanism's goal is to produce answers such that for all I from 1 up to k, the difference between the provided answer and the true population answer is small. So, so the mechanism is going to try to provide answers that are useful in as much as they reflect the population, which may not be the same as answers that reflect the value on the data set. And so we can ask, like, what's the best mechanism for this? And we'll often, for convenience, we want sort of things that work for all analysts, so we'll sort of, you know, put on our computer scientist hats and think of the analyst as an adversary here. And so what we want to know is, I'm going to look at the, you know, for a given mechanism M, what we'd want to be able to say is something like, for all distributions P, and for all adversaries, for all analysts A, the probability that the maximum error is at most alpha is, let's say, at least you know, 99%, for example. You could require and ask for the expected maximum to be small, the expected square, whatever you want. And so this, what this says is that the so we want to find a mechanism for which this quantity is small. So what we really want is like the, you know, does there exist a mechanism that solves this? And what we want is the argmin over alpha of this quantity. And we have various upper bounds and lower bounds on these quantities. They're reasonably close. There's some small gaps there. What we don't know is, we don't know sort of non-trivial impossibility results for this setting, where when we just make a small change to the quantifiers of the setting, which is that we give the mechanism access to the same information that the analyst has about the distribution. So let me explain that just a little bit. So one can imagine that there's some sort of generation algorithm that's some process that's generating the underlying population. And in the worst, the sort of class, the setup that I had before, it's equivalent to say I want, you know, accuracy no matter how P is generated. Okay. But now I can ask what happens if both the mechanism and the analyst know this generation, know the description of this generation process. So they know the same, like, prior, they have the same prior on the distribution. And what that corresponds to in terms of quantifiers is just swapping the first two quantifiers. So we could ask for the kind of the symmetric version of this, where we just say, what we want is that for all generating distributions, there exists a mechanism that now might depend on the prior, such that, you know, for all adversaries, for all analysts, the same thing happens. And again, we might ask for sort of the best rate for the best error for which this is possible. This is a function. In one case, this is going to be a function of n and the number of queries in both cases. So this is, the first one is sort of an asymmetric setting, and the second one is a completely symmetric setting. And essentially the open question is to find non-trivial lower bounds on this second quantity. Okay. So some things are known, and I can tell you offline more about what is known, but in full generality, we don't know anything that isn't sort of just true for non-adaptively posed queries. And I'll stop it.
Yeah, we can allow them to depend on the prior though, because it's not doesn't have to be like one bound that holds universally.
You could also ask for prior specific bounds. That's right. Although those I think we know more about. But you mean for specific priors, I guess.
Well, like sufficiently non-informative or blah blah. Bayesian something.
What's the role of the data? I missed something, I think. If
Data?
you know the distribution.
Oh, sorry. So in here, what's going on is that the mechanism knows that. What does the mechanism get to see? The mechanism only sees X, only sees the data.
It knows the distribution.
No, gen is not the distribution.
So gen is not the distribution. It's like a prior over distribution. So imagine it's a process that generates. So I sample P I sample a description of the population of P. So it's a prior distribution over populations. And now what I want is so the mechanism needs to look at the data. But now we're allowing the mechanism to know the same thing that the analyst does about P. So whereas in this setup over here, if you sort of think of this game theoretically, these two players are playing together against the mechanism. So they're sort of jointly selecting the analyst strategy and the probability distribution at the same time, and it turns out that gives this kind of pair of players a lot of power over the mechanism. And we know how to prove lower bounds, so Steinke and Ullman have the strongest result in that setting. But once we switch this, we know some under lots of assumptions we can say different things, but we don't really have a strong statement. And I think I'm more than out of time. It's a race.
Okay, so I'm Adam Silfan, and the problem I'd like to talk about is about all pairs distances under differential privacy. So if you have a graph, one of the basic functions that you might want to compute is the distance between a pair of vertices. Under the normal notions of differential privacy for graphs, no differential privacy, edge differential privacy, this doesn't make a lot of sense because you can delete a single edge and make a distance go from 1 to n-1, or you can even disconnect the graph. So if we're trying to hide the topology of the graph, it doesn't make a lot of sense to ask for distances. But what does make sense is to consider a setting where the topology of the graph is fixed and publicly known. And the private information consists of an edge weight function. And then we're trying to compute distances in a weighted graph, in the weighted graph. So if we restrict to the setting, so then the next question is what are neighboring weight functions? So sort of one very natural choice is to say that two weight functions are neighbors if they differ by at most 1 in L1 norm. So that'll be the definition we'll use. And under this definition, releasing a single distance is completely trivial. It's a sensitivity 1 query. But the question we can ask is, what if we want to release the approximate distance between all pairs of vertices in a graph? So then we have n² queries. And there's two very natural approaches. Like the first two things you'd try would be you have n² queries. We can do them each privately, use composition. So that gives error roughly n log 1 over delta over epsilon. And the other very natural thing to do is to take each edge and add Laplace noise to the weight of the edge, sort of release synthetic data, and compute distances in that synthetic graph. And that gives error something like n log n over epsilon. So in both cases, so for these simple approaches, we're getting error linear in n. And I have no idea if that's inherent or not. So the question is, does this have to be linear in n? Can we come up with an algorithm that doesn't have this dependence on n, or is there a lower bound? What lower bounds can we get? I don't know a non-trivial lower bound. Maybe we can get a lower bound of n or something weaker. That would be interesting. I should also mention that I do know for two special classes of graphs, we can do better. So, so for trees, we can do sort of exponentially better. All pairs distances in trees, we can get error roughly log to the 1.5 n over epsilon. And I suspect this can be improved to log n. This is very much analogous to releasing all threshold queries, which sort of corresponds to distances in the path graph. So we can generalize that to arbitrary trees. And then the other setting is if we have if we're guaranteed that the weights are bounded. Then we can get error that that looks like sort of root n times m. And I also don't know if this is optimal or if there's interesting bounds for other classes of graphs. So that's the problem. Any questions? Or?
So what's the algorithm for bounded weights?
So for bounded weight, I think it's something like basically you can find a without looking at the weights, you can find a set of vertices. Basically, if you just look at a graph, you can find some set of vertices so that every vertex is not too far from one vertex. So you choose some set S of the vertices that's not too large, so that every vertex in the graph is not far from a vertex of S. And then the distances between vertices in S give you a pretty good approximation for distances in the graph. And then you can sort of tune the size of S to make it work out.
If you don't care about efficiency, can you do the computational efficiency? Can you do better?
If you don't care about computational efficiency, I have no idea. The algorithms I know are efficient, but there might be something better that isn't.